All right, well, good morning, everyone. Hope everyone is doing well. We're going to go through this kind of like we would a class session, but most of it's going to be Q&A time. So I'll have some questions show up on Learning Catalytics. You can respond to them on your machines at home. And, if you have questions, you're welcome to kind of jump in with audio or use the chat feature in Zoom, and I'll try to reference that as we go through it. Let's go ahead and start with just to try to make sure that we are understanding here a little bit about the topics that we discussed last time. So this is a matching question. I want you to match the appropriate definition with each of these terms. So if we talk about something like average velocity or instantaneous velocity, secant line, tangent line, just want to make sure we have those definitions down from last time, and then we'll jump into a applied problem. So I'll give us about, you can see the timer here on the top. I'll give us about 3 minutes to do this question. Get everybody in. All right, you got about 30 seconds left. All right, so here are the results. More than half of us got it exactly right. The matching here, the average velocity is the slope of the secant line to a position curve. So we talked about this in class last time. Average velocity is slope of a secant line to a position curve. Secant line is a line that cuts through multiple points of the same curve. So that would be C matching with this one, a line that intersects a curve more than once. The instantaneous velocity is the slope of the tangent line to a position curve. We're going to use both of these in the question that's coming up. And then a tangent line is a line that matches the direction of the curve it intersects. So these are from last class definitions that we're going to be using today. All right, let's jump into a question. We looked at this function at the end of class last time, and I've changed the interval slightly to make sure that you can still probably do this. So if you understood at the end of class on Wednesday, you should have no problem here, but go ahead and calculate for me the average velocity of the ball with this position function between the interval 0.5 and 1.5. And then we'll take a look at it in Desmos together. You're welcome to use Desmos to do it. You're welcome to do it by hand. I'll give us, let's say, another 3 minutes on this one as well. Remember, average velocity on an interval is the slope of the secant line connecting the endpoints of that interval. All right, you got about 30 seconds. I see that there are 15, 16 of us here this morning. That's a pretty good turnout. I will be recording this so you can go back and review it later if you need to. All right, so most of the responses are filtering in at this point. So let's go ahead and look at the correct answer. The correct answer here is 0. So 50% of us got that correct. 0 meters per second is the average velocity. I want to look at this first by hand, and then I'm going to look at it in Desmos with you. So by hand, what we have is the position function that was given to us. And we know from class that the average velocity on an interval is the slope of the secant line on that interval. And our secant line formula is just the slope formula. So here our endpoints are, the right endpoint is at 1.5 seconds. The left endpoint is at 0.5 seconds. And so we would be calculating this particular value. where we would just plug 1.5 in for the function and see what we get, subtract it from 0.5, see what we get, and so on. If you calculate this, you will get 0 meters per second. Now, what's interesting here is on a graph, you can see this very plainly. So if I go to Desmos and type in S of t equals 64 minus 16 t minus 1 squared, I'm going to get my graph here zoomed out where I can see some things. So let me change the zoom setting, or the zoom for it real quick. So there's my graph. And the points that we're interested in are the points at 0.5 and at 1.5. What you immediately notice about those 2 points is that they are horizontal from one another, so that any line which passes through those 2 points will have a slope of 0. So you can instantly see just by looking at it without even calculating that it would be a slope of 0. But if we wanted to calculate it, you could just say s of 1.5 minus s of 0.5 divided by 1.5 minus 0.5. And that will also give you the same slope of 0. My hope is that you did this in Desmos, kind of the way I have shown here, but looking at the graph, you can clearly see that that would be an average velocity of 0. And the reason that that makes sense that the average velocity is 0 is because the curve is symmetric about 1. So all of the positive velocities that you've accumulated heading toward 1, the opposites in terms of negative velocities happen on the way to 1.5, and they cancel each other out, leaving an average velocity of 0 meters per second. All right, related to this question, but looking at an instantaneous velocity, I want you to tell me the instantaneous velocity of this ball when it hits the ground. So I'm going to give you about 5 minutes for this one. This one takes a little bit more time. So find the instantaneous velocity of that same graph, the graph we were just looking at, when the ball hits the ground. So remember that instantaneous velocity is slope of the tangent line. And remember in class, we approximated slope of the tangent line by looking at slopes of secant lines approaching the point with smaller and smaller intervals. I saw someone typed in the units. Don't do that. It may not interpret it correctly. So if you've already typed in the units, go back and change your answer real quick to not include the units. All right, you have about another 30 seconds or so. All right, so the correct responses on this problem, those of you that have responded, negative 64 is correct. Let's take a look at why. Basically, the problem we have here is we have this rock that's being thrown up. After 1 second, gravity overcomes it, pushes it back down, and it hits the ground 3 seconds later. So this is the curve that you would have plotted in Desmos. If I want to find the tangent line to this curve, the slope of the tangent to the curve at the point t equal 3, which is the instantaneous velocity, basically all I have to do if I'm going to do it by hand is find the slope of the secant line for points that are really, really close together. For example, I might say, okay, well, I know that, 2.999, let's say, is really, really close to 3. So I can estimate the slope of the tangent line, which is the instantaneous velocity. I can estimate that or approximate that by looking at the secant line between those 2 points. So this is an approximation of the instantaneous velocity because it's a secant line, which is an average velocity, but it's an average velocity over an incredibly small interval. So if you wanted to just do this by hand, that's probably your best route. If I switch over to Desmos now, you can see in Desmos, we've got the point here at 3 where it crosses the axis. We're going to look at the velocities as we approach that point. In class, what I did was created a table. And so you've got the x values, which would be time values here. And then for the y values, all I did was put in the slope formula. So the slope formula is s at 3, because the point 3 is the one that we're looking at, minus s at x1 divided by 3 minus x1. That's our slope formula. I don't think I need projector mode. I'll take that off. So that is our slope formula here. You've got the time value, and then you've got s at 3 minus s of x1 divided by 3 minus x1. We're going to look at time values that are close to 3. So we're going to be approaching 3 from the left. So 2.9, 2.99, 2.999. And the closer we get to 3, you can see that all of those slopes are coming back closer to negative 64. There's not really a better way to do that. If you're asked questions about instantaneous velocity or slopes of tangent lines, this is really the only way that you can do this. You're going to have to approximate it until we learn about something called the derivative, which is the importance of derivatives in this course. It allows us to do this without approximating. We can find those values exactly. All right, so that is how to do average velocity and instantaneous velocity. It's two of the bigger things to come out of this first lesson. The material for this being found in section 2.1. All right, let's try another one that's sort of related, but has a slightly different connotation to it. All right, so I'll give you about 3 or 4 minutes here. What I'll tell you is, for this problem, you shouldn't have to calculate each one of these things. Okay, if you're doing that, then you're taking too long. What you should do here is look at this problem graphically and then make up your mind. What I'm asking you to do is rank the following quantities from smallest, which means most negative, to largest, which means the least negative, or positive, most positive quantities. So rank these from smallest to largest for this particular function. So you've got a function where the price of some object leads to some demand D. And like I said, you should be able to do this without calculating anything. I simply want you to rank these 3 things. The average rate of change of demand when the price goes from 100 to 200. How does the average rate of demand change when you go from 200 to 300? And then what is the instantaneous rate of change when the demand is, or when the price is $50? So rank from smallest to largest. All right, and I will give us, let's say 3 minutes from right now to finish this. If y'all have questions, you're certainly welcome to ask. You can do it by audio or by chat.
I have a question, Professor.
Yes.
So is the first choice the highest, right? It's the most rate of change. And third choice, least rate of change?
No. It's smallest to largest. So the first one that you should list on there, and then I think you have a little drop-down box where you can say less than the next one, less than the next one. The first one you put should be the smallest. Now, smallest here could be the largest negative, right? Because the more negative you are, the smaller you are. So just be careful about that. So on your screen, I have a decent look at this graph if you were struggling coming up with the Zoom to take a look at it here. I just used the information in the problem to tell me kind of what the setup was here. I knew I was going out to 300. So I needed to make my horizontal axis at least 300. And I knew that there was a 10,000 in the problem. So I made my y-axis at least 10,000. So that's kind of how you get an idea of what to do with this particular problem. So looking at this graph, you should be able to answer this question. Remember, you can adjust the window by clicking on the little wrench icon in the top right and then changing the x-axis and y-axis limits. You can also zoom in and out by using your trackpad or your mouser or your mouse wheel, or if you're on an iPad, pinching in and out on the graph as well. All right, most people have responded at this point. So let's go ahead and take a look at the correct answer. So about half of us again got it correct. The order that it goes in, well, it's not really showing you here. I'll show you. The correct order is instantaneous rate of change at 50 is the smallest. And then the average change from 100 to 200 is next. And then after that, the average change from 200 to 300 is actually the largest average change. Okay, let's take a look at why that is the case. So if you're here on Desmos, I'm looking at a couple of points, right? I'm looking at the point at 50. I'm looking at the point at 100. I'm looking at the point at 200. And I'm looking at the point at 300. These are all the X values involved. Now, I'm not going to take my time to actually calculate any of these lines or any of the slopes of these lines. I just want us to think about it this way. And in fact, this will probably be better if I actually just sketch this out. So let me go to iPad here real quick. Let me sketch this out for you. We've got the function which looks like this. So you've got price, and then the demand is a function of price as the y-axis. The graph does this. At 50, you've got this point here, then at 100, 200, and on around to 300. Now, the instantaneous rate of change at 50 is a tangent line. So here's the tangent line at 50. Would look something like that. Here is the tangent line, or the secant line, excuse me, between 100 and 200. So the average rate of change would be the slope of the line connecting those 2 points. So that's the average rate of change over the interval from 100 to 200. And then finally, the average rate of change from 200 to 300 would be this line right there. So in terms of ranking them, which one has the smallest slope? Well, the smallest slope is going to be the most negative slope here, which is going to be the instantaneous rate of change at 50. That one has the smallest slope. That is the most negative value. So this is the instantaneous change at a price point of $50. The largest slope in this context, they're all negative slopes, right? And it should make sense that they're all negative slopes, because if you think about how demand works versus price, if your price increases, then the demand for something decreases. So that's why all of these have negative slopes, is because the demand is decreasing as we increase price. That's why this curve is decreasing. In the real world, that's how it works. If you charge more for something, less people are interested in buying it. So the largest slope here is the least negative one, which will be the average rate of change between $200 and $300. So that turns out to actually have the largest slope because it's the least negative. I know that's a little bit backwards in your head, but because these are negative values, the way we think about smallest to largest, you have to think about it in number line terms, right? So if I was to plot the number for each of these slopes, the smallest number would be the number that we have here. Now, not smallest in magnitude, right? So it's decreasing the quickest here. It's decreasing less quick here, and it's decreasing the slowest here. But in terms of the actual number that's involved from smallest to largest, this is the correct ranking. And so the one in the middle is the average rate of change from 100 to 200. So that's the order that you should have had them listed in. Hopefully, if you made a mistake on that, you kind of know where the mistake came from. The important thing to take away from this example is I didn't have to calculate the slopes to answer this question. So on an exam or something like that, it's very common for me to ask questions that require you to understand the concept behind a thing rather than having to calculate out all the things. Now, you could have calculated out all of these, but it would have taken you 10, 12 minutes probably to do that on this problem, and that's way too much time when I'm thinking this is a 2 or 3 minute question because you're just going to graph it and look at it. So you got to make sure that you're doing things in the most efficient way possible in this class. And for me, that's not going to be a ton of calculations. All right. So let's look at another one. So here we have a tank that's holding 1,000 gallons of water. And then we have some data. 5 minutes later, the 1,000 gallons is now 694. Another 5 minutes, it's dropped again. Another 5 minutes, it's dropped again, and so on. So this is data related to something called Torricelli's law, which basically says that if you have a tank full of water, because of the pressure involved having more volume, it's going to drain faster at first, but over time it drains less fast because there's not as much pressure behind the volume. As the volume decreases, there's not as much pressure pushing the water out of the tank. And so that's the situation we have here. We have some data, and what I'd like for you to answer is, if we had a graph V of t that was continuous, that measured the amount of gallons remaining, from 0 to say 30 for 30 minutes, which of these intervals would have the which of these intervals would have the steepest slope? Now, when I say steepest, I don't mean it's not like the last question, right? Where smallest slope, what turned out to be the most negative. When I say something like steepest, I literally mean the magnitude of the slope, not the sign, okay? So if it's positive, steepest is the largest positive. If it's negative, then steepest is the largest negative, or which would be I'm looking at the magnitude here, not the actual number. So the positive negative doesn't matter here. And once again, if you don't want to, this doesn't have to be a problem where you have to calculate a lot. In fact, it's a problem where you can just use physical intuition to help you answer it, but then you should be able to explain that physical intuition. All right, you got 1 minute. Well, actually, it looks like most of us have responded. So I'll give you about 30 seconds or so if you haven't responded. I think there's only one person that hasn't. Yep, and there we go. All right, so the correct answer here is A. The steepest portion of this graph would be over the interval from 0 to 5. So the steepest slope, the highest slope in magnitude would be from 0 to 5. It's decreasing the fastest over the first 5 minutes. Physically, that makes a lot of sense based on what I said about Torricelli's law. Let's look at it mathematically, and I'm going to do this in 2 different ways. I'm going to start with Desmos. And one of the best things you can do in Desmos here is to plot a table and just plot the points. So the points, we know initially at 0, there are 1,000 gallons. Now I know that's not in the table, but that's something that you should be able to infer from the problem. At initially, there are 1,000 gallons. Then 5 minutes later, there's 694. Another 5 minutes, 444. 250, 111, 28, and then we're out after 30 minutes. So let me zoom in on this. You can see we have the data points here. And what the question, if I were to rephrase the question, since the volume is decreasing here, the one that has the steepest interval, given the intervals that we're looking at, would be the one that has the most negative or fastest decreasing. That's the steepest, the fastest decreasing interval. So if I just think about connecting the dots, which I can do if I hold down on this and select lines, I can kind of connect the dots here. Here's what I would think my graph of V of t would kind of look like. If I think about the slopes between each of these points where we connected the lines, which one is the most negative? Well, it's the one from 0 to 5. And I could verify that by going in, and here's my table. I could go in and calculate, you know, what is S of 5 minus S of 0 over 694 minus 1,000. So let me just quickly calculate that in Desmos. So S of 5 minus S of 0 over, whoops, we don't have an S anymore. I don't, oh, actually I can't do that. Yeah, I can. Okay. Hold on 1 second. Missed a step. So it wouldn't be S, it would be V, right? Because we're looking at volume as a function of time. So it'd be V at 5 minus V of 0 over, man, I screwed that up, didn't I? Over 5 minus 0. There we go. So it would be the volume after 5 minutes minus the volume at 0 minutes. So this is the volume after 5 minutes minus the volume at 0 minutes divided by 5 minus 0. So this would be 694 minus 1,000 divided by 5 minus 0. And I could easily plug that into Desmos and figure out what that value is going to be. So 694 minus 1,000, negative 306, divided by 5 is negative 61.2. So this number is the slope of this line right here from 0 to 5. Now, if I want to compare that with the next interval, well, the next interval is the difference between 444 minus 694 and then the times there are 10 minus 5. And you see that that one is negative 50. So that's the next two data points. So we've got negative 61 for the slope here, and then the next two data points are negative 50. So it's a faster drain over the first 5 seconds than it is over any of the subsequent intervals. And you could do that simply by looking at the graph. You could calculate each segment. I want you to do it in the way that is the most efficient, though, which is probably just thinking about it from a physical perspective, sketching a graph of what you think it would look like, and then explaining it that way. Do y'all have any questions about that one? Because it's very likely on quizzes and exams over this material that you're going to get some data in a table, and you're going to have to answer questions kind of like this about what's the steepest area of increase, what's the, are there any places where the average change is 0, things like that. Answering questions based on data. All right, then final question. Suppose that we are given data that when you drop a solid object from rest near the surface of the Earth, the position function for that data is 16t squared. So this is where you're sort of negating gravity a little bit because you're really, really close to the surface of the Earth. You're going to determine a formula which gives the average velocity of the rock at the instance t equal 2 to any slightly later time t equal 2 plus h. So what I'm asking you to do here is to algebraically come up with the average velocity formula in terms of h. So your answer that you enter should be an expression in terms of h, right? So for this problem, I'm asking that your answer be something like, I don't know, 10 plus h, right? That's the kind of thing you should enter as an answer here. But you're going to have to calculate it, right? So that's not the correct answer, but that's the way that you should enter your answer here. Just to make sure we understand what I'm asking, I'm saying your position function is 16t squared. I want to know what is your average velocity on the interval from 2 to 2 plus h. Okay, that's what I want to know. So that's the formula for that is what you should give me. And we don't have much time left, so I'm going to give you about 3 minutes to do that. So I have 2 minutes to show you the answer here at the end. Is the audio quality okay? Is everybody able to hear it okay?
Yes, sir.
Thank you. All right, as y'all are working on y'all's answer, I'm going to kind of start working through it here, and you can kind of correct as we go along. So the average velocity on the interval from 2 to 2 plus h, that's just our slope formula. So it's s at 2 plus h minus s of 2 over 2 plus h minus 2. So s of 2 plus h is s of whatever is 16 times whatever squared. So S of 2 plus H would be 2 plus H, 2 plus H. So this would be 16 times 2 plus H squared minus S of 2 would be 16 times 2 squared. Now, obviously, you'll want to enter a simplified version of that. Okay, so let's do a little bit of algebra here and simplify that and get our final answer. So we're going to FOIL out the top. You've got 2 plus H squared. Hopefully here you remember from algebra class that if you have a quantity squared, you square the first term, you square the last term. So you'd have 2 squared, which is 4. You'd have H squared. And then the middle term is you multiply the 2 middle terms, so 2 times H, and then you double it. So you get 4H out of that. So if I expand this thing squared, this is what I would get. And then minus 2 squared is 4. 4 times 16 is 64. And then in the denominator, 2 plus H minus 2, the 2's cancel there, so you're left with just H. Okay, if I clean up the top, 16 times 4 is 64, plus 64H, plus 16H squared, minus 64, all of that over H. And what you notice is the H's cancel. And from there, we have 64H plus 16H squared over H. All of the terms in the numerator have an H. So I can cancel 1H from the entire problem, leaving me with 64 plus 16H. So this is what you should have come up with. We had, if you haven't responded yet, please do so. You don't have to put in the S of t equals, just put in the expression, not the equation. So this should literally be the answer that you put in. This is something we're going to do more of as the semester wears on, because this is giving me a formula for different values of H. I can instantly find the velocities. In particular, what this formula tells me is as H approaches 0, the average velocity on the interval from 2 to 2 plus H approaches what value? What do y'all think? If I let H approach 0, so I'm letting H get smaller and smaller and smaller, that makes the interval smaller, right? So if H is 0.1, we're going from 2 to 2.1. If H is 0.01, we're going from 2 to 2.01. So as H approaches 0, the average velocity approaches what? What value? 64. Good. Approaches 64, which this then is the instantaneous velocity at time 2. So this is the usefulness of the algebra here, is to give us a formula that we can use to evaluate at different interval widths. So H is kind of the width of the interval from 2 to whatever's to the right of 2. So we're going to do some more stuff like this coming up this next week, and then actually the week after that as well. But it's the sort of the algebraic side of the concepts that we studied in Wednesday's class. All right, that's it for today. I'll see y'all back on Monday. Monday we'll start taking a look at what's called a limit. We'll define a limit, do some examples, and y'all have a good weekend.
You too, sir.